Before we begin 1.8, let's review the main points from 1.7 over solving inequalities. In section 1.7, we learned that the trichotomy property tells us that exactly one of the following has to be true for all real numbers. A must be less than B, equal to B, or greater than B. The addition and subtraction properties for inequalities tell us that if A is greater than B, then A plus C is greater than B plus C, and A minus C is greater than B minus C. And therefore, if A is less than B, then A plus C is less than B plus C, and A minus C is also less than B minus C. When we go to solve an inequality, we always solve with the variable to the left side. And to graph our solution, we use an open circle to show the point is not included. We use a closed circle to show the point is included, and when we have a less than or equal to or a greater than or equal to sign. The multiplication and division properties of inequalities tell us that if our value of C is positive and A is greater than C, then A times C is greater than B times C, and A over C is greater than B times C. And if C is positive and A is less than C, then A times C is less than B times C, and A divided by C is less than B divided by C. But if C is negative, then when A is greater than C, A times C is less than B times C, and A divided by C is less than B times C. And if A is less than C, then the opposite is also true. Moving on to section 1.8, we will be discussing solving compound sentences and absolute value inequalities. Compound sentences use the words and or. And means both, and that our solution will have an intersection. Let's look at an example. If we have the inequality 7 is less than 4x plus 3 is less than 19, we can say that 7 is less than 4x plus 3 and 4x plus 3 is less than 19. In solving each separate inequality, we find that 1 is less than x and x is less than 4. To graph our solution set, we use open circles on both 1 and 4 and shade the intersection between those 2 points. A compound sentence containing or is true if at least one part is true. To solve the compound sentence 3x plus 1 is less than 7 or 7 is less than 2x minus 9, we solve each part separately. There is no short way to write a sentence containing or. We graph this solution set as shown with open circles. Next, we will discuss compound inequalities that contain absolute values. The absolute value of a number is its distance from 0 on the number line. We can use this idea to solve inequalities involving absolute value. If we say the absolute value of x is less than 6, this means that the distance between x and 0 is less than 6 units. To make the absolute value of x is less than 6 true, we must substitute all the values for x that are less than 6 units from 0. So as this number line shows, all the numbers between -6 and 6 are less than 6 units for 0. So the solution set is -6 is less than x is less than 6. But we use open circles to show that -6 and 6 are not included in this solution set. This inequality tells us that 2x minus 7 is more than or equal to 11 units from 0. When we have an absolute value, we must solve two separate inequalities. When we see the less than symbol, we need to remember that we are talking about an and compound sentence, when we see a greater than symbol, we need to know we are going to be using an or compound sentence. For this example, we have a greater than or equal to sign, so we will be using or. To determine our second inequality from an absolute value inequality, we need to flip the sign and the inequality before we graph our solution set. We use closed circles on our values of -2 and 9 because we have a greater than or equal to sign and a less than or equal to sign, and we graph the inequality solution set as shown. If you are confused by this, I encourage you to watch this slide again or follow along closely with the next example. This inequality, the absolute value of 6 minus x is greater than or equal to 4, tells us that 6 minus x is more than or equal to 4 units from 0. We have a greater than or equal to sign, so we are again going to be using or. We rewrite the inequality without the absolute value and keep the sign the same, and then we write it again but flip the inequality sign and add our negative. Notice that when solving these two inequalities, the signs are flipped because we want to express a positive value of x, not a negative value of x. The graph of our OR solution set is shown. Some absolute value inequalities have no solution. For example, the absolute value of x minus 4 is less than -6 is never going to be true. Since the absolute value of a number is never negative, there is no replacement for x that will make this sentence true. So the solution set to this inequality is an empty set. Other absolute value inequalities are always true. One such inequality is the absolute value of x plus 5 is greater than -10. The solution set of this inequality is all real numbers. Can you see why? Think of a definition of an absolute value. If the absolute value can never be negative, then the value of x plus 5 is always going to be greater than a negative number. Please come to class with notes and prepared to ask questions. In your problem set, you will see problems that we did not have examples for in this video. Those are the types of problems that you want to make sure we discuss in class.